Hello coders, welcome to my channel. I am Aniket and today we will discuss the problem from GFG, that is delete nodes with greater on right. Let's read the problem. Given a singly linked list, remove all nodes that have a node with a greater value anywhere to their right in the list. Return the head of the modified linked list. Like if you are given this linked list, then the updated linked list will be like, say you have a 12 and then 15 and then 10 and then 11, 5, 6, 2 and 3. So in this linked list, this node 12 has a greater node present in right. So that node is 15. So you have to delete this 12 because there is a node present in right which is greater than it. So you have to delete 12. Similarly here also 15, there is no greater node present in right. If you check all of them are greater smaller than this 15 because the maximum out of this is 11 and 11 is smaller than 15, so all of them is smaller than 15, so you will retain this element as it is. Then again this for this element 10, there is an element 11 which is greater than it in its right, so you have to delete this 10 also because you have a element 11 which is greater than 10 and present in its right. Similarly here also, if you consider the maximum of this window, that is 6, so 6 is lesser than 11, so you have to retain this element as it is because there is no element present in its right which is greater than 11. Similarly here also there is an element 6 which is greater than 5, so you have to remove this element, and for this 6 there is no element in rights which is greater than it, so you have to retain this. And similarly here also there is an element 3 which is greater than 2, so you have to delete this element. And this is, since this is the last element, so last element will always be retained because for last element there is no element present in its right which is greater than it, so last element will always valid because there is no element present in its right. That's why last element is always valid. So now the updated list will be 15, then 11, and then 6, and then 3. This is our updated linked list after all possible deletions. What is the brute force method to do it? Let's discuss the brute force method. The brute force method is when you are at any node 12, you have to traverse all its right. Like if you are at 12, then you have to traverse all its right. Then you find which node has the maximum value. If the maximum of this window is greater than this minimum, this 12, then you can say you have to delete this 12. Similarly here also, if for this window you have to traverse all of the node to get check the whether there is an element present in its right which is greater than 15. So for every element you have to check whether there is an element which is greater than it present in its right. So every element, it might be possible then that you will traverse the whole array. Then for every element you can traverse the whole linked list to find whether this is smaller than, there is a node greater than this node present in its right. So you, for every element you can traverse the whole linked list. So there are n elements, and for every element you can traverse the whole linked list. So the complexity for this approach is O of n square. Because n is quite large, so this approach give you TLE. That's why you can't do this approach, because n is very large, and for this brute force approach the complexity becomes O of n square, because for every element you have to check all its right element whether there is a element present in its right which is greater than it. That's why, like say for this 12, you find this 12 with this 15, that 12 has a greater elements in its right. What happen if this 15 is present at last? If this 15 is present at last, then you have to check all its right element till 15. Then you will find that 15 is greater than 12, so you have to delete 12. That's why for every element you can traverse whole linked list. So the complexity will become O of n square. So what is the optimal way to do it? Let's discuss the optimal way. So if you carefully see, you want to find the maximum of the remaining window. Like if you want to check whether you have to delete this element or not, so you want to find the maximum of this window, right window. We want to find the maximum of right window for checking whether we have to delete the current element or not. So if the maximum of right window, that is max of right window, is greater than current dot data, then you can say you have to delete this current. So you have to delete this current. But if this is not happen, else, but if it is not happen, then you can take this current node into your updated linked list. Like in this case also, if you found for this 12, if you found the maximum of right window, that is 15, so 15 is greater than 12, that's why you have to delete this 12. Similarly here also for this 15, if you found the maximum of right window, it will give you 11. So 11 is lesser than current node, that's why you have not to delete, you need not to delete this 15, you will retain it in your original linked list, updated linked list. That's why this is the our approach, where if the current data is less than max of right window, then you have to delete this current, otherwise you can take this current node into your updated linked list. So the question is, how can you find maximum of right window in optimal way? Question is, how can you find the max of right window in optimal way? So the optimal way to do it is traverse from right to left. In this case, you will traverse from left to right. So you have to check the right window, what is the maximum. But if you traverse from right to left, then the maximum will be maximum is easy to find. How? Let's say this is our linked list. I will take this link list, this same linked list, 12, 15, 10, 11, 5, 6, 2, 3, 12, 15, 10, 11, 5, 6, 2, 3. So you want to traverse from right to left. So, but the it is a singly link, but it is a singly linked list. So how can you traverse from right to left? So to traverse from right to left, you have to reverse the linked list. Otherwise, you can't traverse from right to left. So you have to reverse the linked list. The reversing a linked list costs you O of n complexity. So now the new linked list will become this. Now the head becomes 3. If you traverse from uh, right to left, then you can easily find your maximum, whether it is lesser than or lesser than that maximum or not. For this last node, if you carefully see, for this last node, what is maximum? Maximum will be the maximum of the whole suffix. So maximum or till this index will be maximum of whole suffix. So you can easily find it how you will do max of max comma current dot data. You always want to maximize your max variable with current dot data. Now firstly the max will be very minimum like integer minimum value. So if you are at this index, then your max will update it to 3. So is this condition hold? Current dot data lesser than max? No. So you have to uh, retain this node as it is. Now if you reach at 2, then the max will now max cannot update because there is already a 3 present which is greater than 2. So why max goes to 2? Because we want to maximizing our max. So if you call max function with 3 comma 2, so max will remain as it is with 3. If you compare this 2, is 2 is lesser than the max? Yes. So you have to delete this element. So you have to delete this element. Then your max will same as 3. Now the max will update it to 6 because for current element if you call 6 comma 3 maximum, so maximum will update it to 6. Is this node is lesser than this maximum? No. So you have to retain this element. Now again if you call maximum for this node 5, the maximum will same as 6 because if you call 5 comma 6, then 6 will be same as stored in maximum. So is for this node maximum is uh, greater than this node's value? Yes. So you have to delete this node. Similarly if you go to 11, you are not need to delete this 11 because the maximum is only 11 and it is not lesser than 11. So that's why you don't delete it. Similarly, when you go to 11, 10, maximum is 11, so you have to delete this. Similarly, when you go to 15, the maximum is 11, maximum is 15, so you can't delete this 15 because 15 is equal to 15, not lesser than 15. Similarly, if you go to 12, the maximum is 15, so you have to delete this element. In this case, the new linked list will be 3, 6, 11, and 15. But you consider reverse in the initial step, but you consider reverse in the initial step. That's why you have to consider one more reverse to get the original answer, because of reverse will give you the original answer. So after that you have to reverse one more time. After doing this operation you have to reverse one more time. So you do reverse operation with O of n, and then deletion operation will also cost you O of n, and the again reverse operation will cost you O of n. So you can do this problem with O of 3n, that is approximately O of n complexity. So you can easily do this question with O of n complexity, which will accept it easily. I hope you understand the intuition. Now let's discuss the code. This is my simple Java code for this problem. Let's make it white. So this is the structure of a node for a linked list. It contains a data and a next pointer. Similarly, first we calculate the reverse of head linked list, and it will reverse our linked list. Reverse the linked list and give the updated head. Let's say if the linked list is ABCD, then after reversing, now the linked list will be DCBA. So in this case you have to return this D head, D as a head. That's why reverse head will give you the reverse head, that is this element, this node as your reverse head. Then you initialize your temp with reverse head, and initialize your maxi with integer dot min value, and prev as null. Similarly, you will always maximizes your maxi, if whenever possible, maximize your maxi variable whenever possible. What it will give you, it will give you the maximum of right window. So it will give you the maximum of right window. If temp dot data is lesser than maxi, then you have to delete this temp. So what you will do, prev pointer will be here, temp pointer will be here, and you want to delete this temp. So what you will do, prev dot next will point to temp dot next. So now this will the node where the temp will point now. Now the prev dot next will point temp dot next, and temp will be go to the temp dot next. Similarly, temp will go to the temp dot next. Now the temp will point here, and you have to do this continue statement because you have to check this node also whether it is lesser than maximum or not. So you want to do the same operation again. So do the same operation again for checking because it is a new node. So you have to check this node also. That's why we do this continue statement, jump to the while loop again. Then if it is not present, temp dot data is lesser than maxi is not present, then you can take this element in your updated linked list and simply do prev, like if it is this case prev and temp, and you don't want to delete this temp, then in this case you will do prev equal to temp. Now prev will point here and temp will go to the temp dot next. Now temp will point here. Now you will check this temp again. Similarly, after doing all of the operations, you will return your reverse of the reverse head as your answer because reverse of reverse will give you the original linked list. This is the code of the reversing a linked list. If you don't know how to reverse a linked list, if you the head of the linked list is given to you, then please go and watch a video for reversing a linked list because it is very important. I hope you understand the code of my and the intuition behind this code. Please hit the like and subscribe button so that you can't miss any PUTD explanation in future. I hope you understand my code. So thank you for watching my video.